What's going on in the Algebra Bros? It's Mr. C here, and in this video I'm going to present to you the Wronskian. Pretty cool thing in linear algebra in my opinion. Alright, so just to kind of catch us up to speed on, where we're at, we've already seen how to deduce whether or not a set of vectors is linearly independent, as well as a set of polynomial functions. But keep in mind that there are many other types of vector spaces that are not consisting of, or that don't consist of vectors nor polynomial functions. We might have a vector space consisting of functions that are not polynomials, but rather transcendental, such as logarithmic or trigonometric, and so on and so forth. So, how would we be able to deduce whether or not a set of those types of functions is linearly independent? Well, it turns out that you'll need something called the Wronskian, and the Wronskian is a function that is the result of evaluating a determinant. So let's go ahead and get to the definition of it. So let's suppose that f sub 1, f sub 2, and f sub n are functions that are n minus 1 times differentiable on the set of real numbers. Then the following is called the Wronskian of these n functions. I'm going to write w of x equals, and in the first row of this determinant, we will insert the functions that are presented to us, and all of them. So to be as generic as possible, let's say it's f sub 1 of x, f sub 2 of x, all the way down to f sub n of x. I'll close off the determinant. Now, we need these functions to be n minus 1 times differentiable because recall that in order to take the determinant of a matrix, the matrix needs to be square. So essentially what happens is we continue to take the derivatives of each of these functions until we've populated a determinant of a square matrix. So in the second row, if we need it, we'll take the first derivative of f sub 1 of x, the first derivative of f sub 2 of x, all the way down to the first derivative of f sub n of x. And like I said, we continue doing this until we have enough rows in the determinant to where we can actually execute the determinant. So in the third row, we'd have the second derivative of each of these functions. And we'd continue doing this, and this is to be as generic as possible, until we get to the n minus 1th derivative of each of these functions. Now, because this determinant is populated with functions and their derivatives, as you might expect, once we evaluate the determinant, we're going to get some function, which is why I wrote the Wronskian as function notation, capital W of x. And with any function, you can plug in any value for x. Notice that we are saying that these are differentiable on the interval negative infinity to positive infinity. And here's the deal. If the Wronskian is not identically equal to 0 on the real numbers, then the functions form a linearly independent set. So that implies two facts. Right? The first fact is this. If the function that we get after we evaluate the determinant is not identically equal to 0, then we have linear independence. So essentially, it might turn out that when we do the Wronskian, everything cancels out to give you 0, in which case it doesn't matter what you plug in for x, the result will always be 0. Okay. This fact says that if things don't cancel out to give you the number 0, then it's linearly independent. The second fact is a little more practical. If W of C is not equal to the number 0 for some C that's an element of the real numbers, then this also implies linear independence. So let's say that the Wronskian doesn't turn out to be identically equal to 0, but rather it's some function. If we can find a value of x that once plugged in gives us something that's non-zero, then we know right away that the set of functions forms a linearly independent set of vectors. Okay, so in the next couple of videos I will work out some concrete examples. As always, if you have any questions about this one, feel free to let me know. Otherwise, thanks for watching.